All right, so let's resume this discussion over compact set. So, or compact set and sequentially compact set. We already have shown that a compact set is already always sequentially compact in a metric space. Actually, we could extend the notion of sequentially compact even if the set doesn't have any metric. This is not the purpose of this course, but we could do that, and a compact set is always sequentially compact. Now, what we want to show is the reverse. This statement in the reverse direction, sequentially compact implies compact for metric space. For that, we need to introduce the first definition, which is quite important in topology, is the notion of being totally bounded. So, again, this is the same setting. We always assume that we are working on a metric space and we won't change it now. And we take a set K in E. K is not necessarily compact at this stage, closed or whatnot. I don't say anything. But we say that K is totally bounded, and I will use for a shortcut these 6 letters, if and only if for any epsilon positive there exists a finite numbers of elements in K. So there exists, I should say, there exists a P and there exists x1, x2, xp in K, such that the union of the balls centered at those points and of reduced epsilon, the same epsilon that I fixed, covers K. Right. So of course, if we have this property, it means that K is bounded, yes. But if you say saying that K is bounded is a weaker condition. Right. So in the spirit of looking at sets in the finite dimension, so in Rn in general, we equipied with the Euclidean metric. Bounded implies totally bounded. This is something which is quite easy to say. I will probably say a few words about that later on. I mean, to summarize the idea, how we can end up doing the retrieving the fact that closed and bounded implies compact for the standard for the Euclidean topology in finite dimension. But let's go back now to this notion. So I'm going to state now the following proposition. F is sequentially compact, and we know what it means. Sequentially compact, that means that for any sequence defined in this set K, this sequence admits convergent subsequences, and the limit of this subsequence is in K. So we have stability by means of limit. Then I claim that K must be totally bounded. Right. How am I going to prove this proposition? I'm going to prove it by contradiction. I'm going to assume that K is not totally bounded. And that's what I'm saying. We should get a contradiction at a certain point. You will see it will come quite fast. All right, what does it mean that the set is not totally bounded? It means this. It means that now, writing the negation of that sentence means that there exists an epsilon positive, such that for any integer p and for any finite number of points in K, the union of those balls centered at xj from j equal 1 to p, those balls centered at xj and of reduced epsilon, this union doesn't cover completely K. Or in other words, it means that there always exists a y in K that's such that y doesn't belong to this covering, in other words. Alright, so let me now erase the top of the board. So what am I going to do with this assumption now? I'm going to construct a sequence which should admit, therefore, a convergent subsequence, because K is sequentially compact, remember. But you will see that based upon the construction I will be allowed to do because of this statement, well, the sequence won't have any convergent subsequence. All right, so how do we do this? So maybe I should make a picture here on the right and see what it takes. So this is my set K. I take any point. So at number 1, I take a point P1 in K. All right. So I should not call it P because this could be confusing with this guy. So let's call it Q. All right. or actually x1. I take it back. Do I need to? Yes, I can call x1. Yes, x1. That makes sense. Sorry. Okay, I take x1 anywhere I want in Q. Well, this sentence I'm going to apply this. There exists an epsilon, so okay, well then this means that the ball centered at epsilon at x1 and of radius epsilon does not cover K. Now, of course, it's a single union, but it doesn't cover K. Otherwise, this contradicts this sentence. Well, this means that I can choose K2 not belonging to the ball centered at x1. That is, in other words, that the distance between x1 and x2 is bigger than epsilon. That means this. Bigger or equal. And x2 belongs to K. Oh, I mean, all the point, actually, I should not say, I don't need to say that all the point I'm going to choose are going to be in K. Well, claim the union of B xi at index epsilon from I equal 1 to 2, from I equal 1, sorry, from I equal 1 to 2, does not cover K. Again, because of this statement. Okay, let x3 not belonging to this union that means that it doesn't belong to the first ball, it doesn't belong to the second ball either. So that means that the distance between x3 and x2 is larger than epsilon, and the distance between x3 with x1 is also bigger than epsilon. So far I've constructed 3 points which are of distance at least epsilon, and for which the union for which the last point doesn't belong to the union of those guys. Alright, so now I need more space. Let me erase this. Well, you see the induction, how I'm going to do that. By induction, I construct x1, x2, xn, right, such that the distance between xi, xj, and xi from I different than j is always bigger than epsilon, and xn does not belong to the union. So more precisely, not that necessarily, simply the union from I equal 1 to n of b epsilon xi doesn't cover K in virtue of this statement. Alright, so this means that, you see, I can always construct such a sequence. For any n I construct by induction such a sequence. And now I claim that we have a contradiction because I'm going to state 2 things. Constructed above must satisfy two properties which will be contradictory, except xn admits a convergent subsequence. Well, remember, I write subsequence by subsec, like this, and the distance between xi and xj is always bigger than epsilon for any pair of integer ij belonging this time in n. Well, I claim that those 2 claims are contradictory. Why? Because if xn admits a convergent subsequence, that would mean That will mean what? That will mean that for any new positive, first of all, let's assume Xn admits a convergent subsequence, and let's call it X and K. So that means that for any new positive, there would exist a K bigger, no, not K, I will say a capital, a little m bigger than 1, such that for any K, so little k, so I should not call it K, it's dangerous with this notation. Let's call it L if you don't mind, guys. For any L bigger than m, well, and for any m bigger than n, and for any n, so I need two guys. For any L bigger than m and n bigger than m, well, this sequence must be of Cauchy type at least. The distance between x n, oh Lord, that's not good, that's not good, let's not call it n, let's not call it k, let's call, s, right, that's bad. N, s, and x, n, l is less than nu. Yeah, I'm just saying that a convergent subsequence is a Cauchy subsequence. But this contradicts now if you take nu equal epsilon divided by 2, for instance, then we must have this. Right. But this contradicts the second line. It says, well, two points which are different must have a distance at least bigger than epsilon. So it contradicts this guy. So that means that the sequence I've constructed not only is not does not admit a convergent subsequent, but the sequence is not of Cauchy type. So this ends the proof of the proposition. Actually, this proposition goes in the reverse direction. So let me state the proposition in the reverse direction. K is totally bounded. It means that for all xn in K, xn admits a subsequence not necessarily converging, but of Cauchy type. So actually, what I've already done is this. What I'm asking you to do as a challenging exercise. Actually, it's not completely easy. So I let you think about that. Left-in exercise. I want you to think of this. How would you do that? Right. Advice. Look at what it means to be totally bounded for epsilon equal 1, then for epsilon equal 1/2, then for epsilon equal 1 to the power 2 to the power n, and try to construct a sequence out of this, and you will see. So that's an advice. So try to do this exercise. It's a good one. It's also something that we sometimes like to put in the qualifying exam. So make sure that you're capable of doing it. That will be, it's a bit challenging, but it's not so hard. All right. So I don't need this proposition in that sense. What I need, I repeat, I need it in the other direction. So if it is totally bounded, no, sorry, if it is sequentially bounded, then it's totally bounded. Now, let's put another proposition. So So this proposition intends to go a little bit closer to my goal. I want to show that if I take a set K, which is sequentially compact, it is compact. So I'm going to start to consider covering of K. And I want to say, well, from this covering, I can deduce a finite covering. All right, so how am I going to do that? So assume K included in E is sequentially compact. And let the union of I belonging to I of OI be a covering of K. Then the claim of this proposition is that there exists what we call a Lebesgue number. What do I mean by this? Let me more specific. There exists delta, and this is this Lebesgue number indeed, positive, such that for any x in K, there exists I in I, so a member of the index, such that the ball centered at x and of reduced delta is included in this OI. So maybe say OI0 or OIX maybe. Let's say OIX. Depends on the choice of x, of course. So in other words, let me reformulate this by the words that everybody will understand in a non-math way. Take a covering of a sequentially compact set. It tells you, well, there exists a radius delta such that pick any point you want in K, the ball centered at this point and of radius delta is always included in at least one of those guys, one of those OI. All right, so let's now prove this proposition. And the proof again is going to be using obviously the sequentially compact aspect of K, and we're also going to do that by contradiction. All right, so prove by contradiction. Assume such delta does not exist. So that means what? That means that I've said that this sentence is not true, in other words. I mean, for all delta positive, there exists always an x, so I'm going to say x, that depends upon the choice of delta, of course. That's always true. Once I've chosen delta, there exists an x that depends upon the choice of delta, such that for all I belonging to I, the ball centered at x and of reduced delta is not included in this OI. That's what it says, that this Lebesgue number does not exist. All right, so now what are we going to do? We're going to discretize delta. Take delta equal 1 over n. For each of these delta, there exists an xn belonging to K, of course, such that for all I belonging to capital I, the ball centered at 1 over n and centered at xn, that point, and of radius 1 over n, isn't a member, sorry, I'm going to try. No, it's not contained, sorry, in any of those OI. That's what it says. Oh, well, it's good, you know, by discretizing, by making a discretization. Wow. By making a discretization of delta by 1 over n, I've constructed a sequence. Well, once I have a sequence in a sequentially compact set, we immediately deduce that we have a convergent subsequence. So let me erase here. All right, so let's xn, not nk but nl, or l equal 1 up to infinity. Well, this is better. Be a convergent subsequence. Well, that means what? That means that xnl converge to a point. So how am I going to call this point? I'm going to call it y. Why not? Of course, it belongs to k, as L tends to infinity. Now let's make a picture. This is, so let's say this, okay, so this is k, like this. This is y, the point where the sequence converges. Now y, there exists certainly an IY such that y belongs to OIY. That's quite clear. And I can even do even better. There also exists a new positive such that the ball centered at y and of radius nu is included in this OI. So let me make a picture. Y belongs to K, so since K is covered by those openings, what I'm saying is that there exist. So I make it big purposely so that we see things. Otherwise, if we really zoom, and normally this should be. You have to think that this blue ball is very small. And there exists, let me put it in red, a true ball by means of a metric, which is completely included in let me do it in blue, so let me do it in blue, in capital ORY. Alright, so this is something which is quite clear because you have a point in the set is covered by open set, and the open set you can put a ball in an open set by definition. Don't ask me how large nu is, don't ask me which I it is, I have no idea, but those guys exist. Now, I claim that you're going to start to see why we have a contradiction. Because y is a limit point of this subsequence. So this means that in this ball centered at y and of radius nu, I should see a member of the sequence, let's call it xm, right? xm. I don't know which integer it represents, because you see this is x1, x2, x3, x4, and so forth and so on, where each of those xj are constructed from the existence of, from assuming that the ball centered at xj and of radius 1 of the j is not included in any of those OI. All right. Okay, so now, how am I going to finish this? So I need to erase a little bit here. Let me erase this. Now, from this, I'm saying take M sufficiently large take, I should say, L sufficiently large such that the number n index L, which I call M, so NL, just a question of notation here. NL. Such that the ball centered at one over m, centered at xm and of radius 1 over m is completely included in the ball centered at y and of radius nu. Yeah, this is clearly possible. Nu is something which is fixed because y is a point, as I said, in K. It belongs to one OIY, so I'm not going to change this OIY anymore. That's an open set. This is a ball which is fixed with a fixed radius, but now I have two freedom to make xmen closer and closer to y, and the ball centered at y, centered at xn and over ym, even closer, even smaller. So let's verify that this is possible for L sufficiently large. That means for M sufficiently large. I just want to make sure that M is an element of index of the subsequence. That's the only thing I need to check. But it is always possible because a subsequence always takes into consideration infinite numbers of integers. So I can take that index here as large as I want. All right. So does this thing make any sense? So I want to make sure that if a point Z belongs to this for M sufficiently large, then Z belongs to that. That's what I want to do. So if the distance between Z and XM is less than 1 over M, then definitively that is what I have to show. So to show then the distance between Z and Y is less than nu. Less or equal than M, less than M, strictly, sorry. I could have written sometime the distance between 2 points which are more less or equal. I meant less strictly. Please correct me. All right, so is it possible, this? All right, so what is the distance between Z and Y? Oh, that doesn't work, this one. What is the distance between Z and Y? This is what we have to fix. This is less or equal than the distance between Z and xm plus the distance between xm and y. Well, this quantity here, it is less than 1 over m, and since I can choose m in this range, so m is equal to nl, this can be less than nu divided by 2, as long as L is sufficiently large. Do you remember x and L tends to y? So that means that there exists an L bigger than 1, such that this guy is less than nu divided by 2. But that's badly written, sorry. All right, Well, now we take M sufficiently large in such a way that this is less than nu divided by 2. And you see that the distance between z and y is less than nu. And this means that if a point is here, it should be here. And that means that this ball here, centered at 1/m and centered at xm, is included in this blue in this red ball. But if it's included in this ball, it's also included in OIY. But that contradicts the thing we said in the first place, that it contradicts the statement we have in the first place, that the ball centered at xm and of radius 1/m is included in none of those elements of the covering. Contradiction. So this means that this Lebesgue number must exist. Alright, so now I'm in position to answer the final proof. And based upon those two propositions we had before, this is a quite direct proof indeed. Okay, so theorem. Sequentially compact implies compact for metric space. So in the spirit and in the frame where we are looking at sets which are included in a metric space, otherwise it might not be true. I strongly use the notion of metric. Alright, so let K included in E, K is sequentially compact. And let's start by making a covering. So let's a union of, I still want to say OI, that's fine. OJ, from J belonging to a set of index which I call J, just change a bit the notation now for a change. Cover K. Now it tells me, the very last proposition I said says there exists a delta positive such that for all x belonging to K, the ball centered at x and of radius delta is included in one of the OI, so OIX. Alright, so this means what? This means what? This means what? This means what? This means that I have the following chain here. K is included in the union from, I like to say x belonging to K, of B delta x. But this, all of those guys, since this is also included in the union of J, including in J, belonging to J, of those OIJ. All right. Okay, but the good news is I have this delta. Now, I have this delta, that's good. And now what I'm going to do, I'm going to use the fact that K is totally bounded. We also know that K is included in the union from, let's say I'm going to call it L again, L equal 1 to P of B. So I'm using, in other words, I'm using here the fact that the set is totally bounded while replacing the letter epsilon by delta. So I choose now epsilon equal delta, and then it says I should find a finite number of those points in K in such a way that the ball centered at all those points, XL, and over radius delta, must contain K. So that's here by, since K is totally bounded. So maybe I should say this, since here, since K is totally bounded, I must have this. But observe one thing, this writing is a sub-covering of this. And therefore it's also included in the union of, sorry, how should I say this? Yes, it is included in the union from L equal 1 up to P of the OIJ XL in the way I define it. So this means what? That means that I've constructed a certain hierarchy in the covering. I start with the covering in the first place. I got this Lebesgue number. Tells me that for any point I can find a ball centered at delta and centered at this point is included in one of this guy. Alright, now I use the fact that K is totally bounded, take this delta and express the fact that K is totally bounded with respect to these guys. So I have a finite number of points, x1, x2, xp. So I construct this covering. But this covering here, each of those balls belong to one of those OIJXL. So I get this covering, this extra covering indeed, but it's still a finite covering, and it's a sub-covering from this one. This ends the proof of the theorem. K is sequentially compact. It implies that from any covering I can deduce a finite sub-covering, exactly that way. Now, quickly, I'd like to say a few words about how we can revisit the proof, which is, I think, Hein theorem. I always forget the name. I mean, essentially, that in if you are looking at a set in Rn, a set of Rn which is closed and bounded is immediately compact. Well, it is sufficient to show that any closed and bounded set is sequentially compact. All right. So what is the structure of this proof? Take a set in Rn. So you really have to think that it's like this. To show that it's compact, it's sufficient actually that the square, right, or the box that includes this guy is compact. If this is compact, since it's closed and bounded and closed, a closed set in a compact set will automatically be compact. So the goal is only to show that cubes in Rn are compact. Take it back, sequentially compact. Now you take a sequence, so you have an x here, which is equal to x1, xm, so Rm, that's the definition, right? Taking a sequence of this, I mean, I'm also to taking a sequence of each of those components. Now, I claim this is something that I would like to really rephrase it as an exercise. If you have a sequence of vectors converging, if and only if for any component j equal 1 up to m, the x, so how should I say that, xj index m converges. So therefore, this means the following. If I want to show that if I take a sequence of points here in this box and showing that there is always a convergent subsequences, it is sufficient to show that we have always a convergent subsequence for each of the components. Now you have to pay a little bit attention. It's not over yet, because you will find a subsequence for the first component. Then you have to re-inject the integers for the second component. But the second component is going to tell you that you are considering yet again another sequence of points on the second coordinate. The second coordinate belongs to the interval, because I'm looking at the product of intervals. It's a cube, right? So I should say it's a cube C. This is I1 cross I2 cross IM. Maybe it's better to say this. And where I1, I2, and IM are just closed, bounded interval on R. So you got a, I repeat, you got a sequence for the first coordinate, you have a subsequence that converge. Take the corresponding set of integers that index this sequence. Look at what it takes for the second coordinate. Well, this is not necessarily converging, but it's going to converge for a subsequence. So take the corresponding set N2 for which that subsequence converge. You are observe that you have taken a subsequence of a subsequence, but it's a subsequence of a subsequence for a subsequence which already converge. So a subsequence still converge. This is something that I already said. A subsequence of a convergence sequence still converge and to the same limit. It was one of the exercises that I set up for you before. So you do it for x2, for x3, for xn. So all in all, you can set up easily a set of index of integer in such a way that all those components will converge. All those subsequences will converge to a point in the cube. All right, so as I said, it is sufficient to show that each of those components would converge sequentially. But an interval which is closed and bounded in R, remember, if we take a sequence, if we take a sequence in this interval, I could formulate Bolzano-Weierstrass if you want, say that there is always an accumulation point. But on the other hand, you can take the limit sup and the limit infimum, and the limit sup and the limit infimum of that sequence will always guarantee that there is always a convergent subsequence, thanks to the theory that we have developed during the video. All right, so this means what? This means that every real interval, is sequentially compact, meaning that any cube like this, as long as it's a finite number of cubes, observe this is really important that I take here a finite number of cubes, is still sequentially compact. If it's sequentially compact, any closed and bounded set inside this cube will be sequentially compact for the same reason. And therefore, since it is sequentially compact, it will be compact. And this ends essentially a review of the proof that any closed and bounded set in a Euclidean space of finite dimension must be compact. Where did I use the Euclidean thing? Here, exactly here. Saying that the sequence of points converge, it implies that each of the components converges. And this is something that I asked you to verify before. It's easy, it's just a question of what does it mean that the distance between 2 points by means of the Euclidean distance. It means that the distance of 2 points being small for the Euclidean distance, it means also that the distance between 2 points for the norm or the supremum is also small. And this is precisely what we need. And this essentially ends what I wanted to speak about. This ends this module about topology. In the next module, we're going to start talking about function, define all those metric space so they could be connected, compact or not, and we'll see what we can do. We will also see sequence of function. We'll see the notion of continuity, absolute uniform continuity, dealing also with uniform convergence. I will talk about the Ascoli theorem and the Stone-Weierstrass approximation theorem. That's where I will stop the next chapter.